Hey Professor, how are you doing today?
All right, how you doing?
I'm doing good. I had a question. I was wondering, did you happen to see my email from yesterday?
Let's see. I probably did not. Let me double
Okay,
check.
I
No,
can
I
I can
didn't.
explain a little bit. So I logged into Pearson yesterday,
Uh-huh.
and the course is like completely gone, like not even listed in my inactive courses. It's just not there anymore. So I wasn't able to get the homework done, and I it's still not popping up. Did
Okay.
you
Are you going through Canvas or are you going out?
I'm going through the independent website, yeah.
Okay, yeah. So you should never access it that way. Always go through Canvas by
Got
going
it.
into my course and then click on Pearson Access. Give
Okay,
that a try right now while you're here. Let's see what's going on with that.
got it.
Another person came in. Are you seeing that now?
Still working on it here.
Gotcha.
Oh, yeah, there it is. Okay. Thank you so much. I did
No
have a
problem.
question. Am I able to make up chapter five then? Since I wasn't able to
Yeah,
miss that.
just let me know when you're done and I'll give you the credit back.
Got it. Thank you so much.
You're welcome. Thanks, Miguel. Everybody else, please take the time to chat your first and last name. Feel free to ask me questions. We still got about 3 more minutes before class starts. Uh, All right, we're getting there, folks. Getting there. All right. Well, it's about time to start. Looks like we got a pretty good number of people. Anybody have any questions before we get started? Please go ahead and chat me your first and last name as well. But anybody have any questions? Oh, there we go again. All right, so I guess that's a good sign. So remember, folks, y'all have this week to do your first face-to-face test if you didn't get it done already last week. Of course, if you did get it done already last week, you actually get to take it again if you like, or you can just keep the grade you had. That's fine. I tried to make the new test easier. Hopefully it is, but I will, just because this was something I did. I will give you the higher of the two. So if you actually did take that first one already, and you do worse, I'll give you the higher of the two. So don't worry about that. Maybe that'll make you feel better. That needs to be done. I think I set this up to be done by Sunday at 11:59 p.m. But if anybody needs that Monday thereafter, which is not this coming Sunday, but or not today, but a week from today, if you need that, let me know. I might be able to stretch it to one more day if necessary. Uh, Does anyone have any questions about any material, syllabus, grades, any of that kind of stuff? Yes, Jennifer.
You have it set to the 16th.
I do have it set at the 16th, and that is Monday.
That is in 2 days.
Oh, no, that's different. Okay. Thank you for letting me know that. Actually, it might be because that's the old version. Let's double check that quick.
It says new
Oh, yeah,
FTF.
that's that one. Well, thank you for doing that. This would have definitely resulted in me getting a call from the student center and me having to, or from the testing center and me having to fix everything. So,
They asked what number it was. That's what I give them, right? What you have listed in Canvas.
yes. Yeah, that would work.
Yeah. Okay, cool.
Okay. So I've now got it set to the 20th. Oh, I know why. It was the 16th because I copied it over from my lecture class. That's why it was. Okay. I was wondering what the heck was I thinking? But then I noticed what time it was, and clearly that's consistent with the fact that I had lined it up for that class. So I think this is good. Thanks, Jennifer. I do have it now set. Anybody else have any questions? Oop, another person came in. Now, is that all you had, Jennifer?
Yeah, that's all I had.
No problem. All right. So last time we had finished up working, various problems with friction, centripetal acceleration, free body diagrams, Newton's three laws of motion, which was, an object in motion tends to stay in that state of motion unless acted upon by a net external force. That was Newton's first law, F equals ma. That's Newton's second law. And then for every action, there's equal but opposite reactions, the third law. And we just saw a bunch of different ways to not only set up such problems and free body diagrams for such problems, but also little tricks of how we solve systems of equations. So for instance, in the Atwood machine, we saw that we can add two equations together, especially when they have, a t in one equation and then a minus t in the other equation. So if we add the two equations, the t and the minus t automatically cancel each other out. That's kind of nice. In one case, for instance, when we were doing the fuzzy dice, we were able to see that if you divide one equation by another equation, that eliminates a variable as well. So a lot of good stuff, a lot of good techniques. And though I'm telling you, in principle, you can do all these different things, use all these different techniques to solve for systems of equations. generally speaking, the way I do it is the way that works most of the time. So you don't have to actually think of this big universe of all the ways you can solve problems. You can just think, well, evidently, just about every time he does it, he uses the same technique. So maybe I should try this technique until I run into something that I can't do it with. And that's really what you should be doing, just to feel out what's the easiest ways in certain situations, and to slowly, step into the universe where you're going to solve your own problems from scratch. So now we're going into chapter 6, which is on gravitation. More specifically, the chapter is called Gravitation and Newton's Synthesis. Okay. So what I want to tell you about this is uh, before Newton, oh, I think I can't stop yawning. Sorry about that. Okay. So before Newton had come along, we had an ongoing problem. Specifically, Aristotle and Plato and various people had worked out models of the universe. And for them, the universe was basically the seven bodies that we know of, which is why we have 7 days of the week. Sunday is from the sun, and Saturday is from Saturn, and so on and so forth. That's literally why we have a 7 day week, is because there's seven heavenly bodies that we think of. And we can trace each of those weekdays names back to that planet in a language. So that's the origins of our 7 day week. But they had come up with an idea with those seven bodies, as well as about, 7, 8, 9,000 stars. And that was their idea of the universe, because they didn't understand that we were actually looking at a very small sphere centered on us that happens to be a itty bitty part of a really big galaxy. And in fact, there's, billions, hundreds of billions of galaxies beyond that. They didn't know all that. So when we say universe and we're talking about this history thing, they just literally mean our solar system and the nearby stars. And they had made a model, and various ancient Greeks, for instance, had made arguments against the model. For instance, they actually imagined that maybe the Earth is not the center, but maybe the sun's the center. And they said, well, if that's the case, then we should experience parallax, meaning when the Earth is when the Earth is, say, on one side of the sun and looking at a distant star, it should see certain stars in that star's background. But then when the Earth is on the other side of the sun looking at that same star, you've got a slightly different angle and you'd see slightly different background stars. Really, what it looks like is, it looks like if you were to take a photograph of the actual stars that you see, you would actually see the star that we're focusing on in one spot, and it would move a little bit between that photo and the next photo. That's parallax. And they figured if we were actually orbiting the sun, then we should be able to see that. Or the universe is so big they couldn't even imagine how big it is. So they looked really hard. They tried to measure parallax, from one year to the next, and they never could measure it. And then that left them with the other argument, which was either the universe is really, really big, like so big we can't even imagine it, or we're not moving. Well, rather than assume that the universe is that big, they went with we're not moving. So it had us at the center of the universe, because it sort of feels like that. I mean, we talk about the earth, or excuse me, the sun rising and setting. We talk about all the planets rising and setting. We talk about the stars rising and setting. So it really is centered as if we are the center of the universe. So it certainly looks that way. And over time, it became obvious that there were problems with that. But Aristotle had come up with very specific laws of nature. Aristotle was sort of the first really big brain that we have a history of, a fairly complete history of. And what he did was he put logic and reason as the centerpiece of his science. And he had certain premises that everybody just obviously agreed with. The problem with logic is logic can get you from one correct assumption to another, to another, to another, to another, as long as you start off with correct premises. If you don't come up with correct premises initially and you're basing all that on that, then your logical steps can lead to something that's equivalent to that original premise, but in fact is not true at all. And that's what happened here. So he basically had imagined the scenario where basically the universe was made up of four elements, five if you count the heavens, and that's earth, wind, fire, and water. And all those objects had a certain way of moving. They either experience natural motion, which is the element of which an object's made is trying to get back to its natural place. So, for instance, the reason why you pick up a stick off the ground and you let it go and it falls is it's actually falling and doesn't require any force because that's natural motion. And what it is a tree limb is made of earth, and the proper place for earth is at the center of the spherical earth. So, yes, by the way, Aristotle did, long before Columbus sailed the ocean blue, knew that the earth was spherical. Okay. That's a common misconception that from what we get from grade school. But, I'm certain there were certain laymen that might have thought the planet was flat, but I don't think there was very many. There might have been a lot. Who knows? But the main thing is the major science people, the people that were doing discovery and were educated and leaders and stuff like that, they did not believe that the Earth was flat in large part. Okay, so that position as the Earth being the center became something really important, even more so than just the laws of physics, because ultimately, when you build all of your understanding of the scriptures on what Aristotle taught us, then all the weight of the scriptures is behind what Aristotle taught us. So it's a lot harder to just shake Aristotle once we've got our entire worldview based on that, which is sort of what happened. So, we had before that, like I said, Democritus, I think, was the one that suggested the Earth might be not the center, but might be orbiting around the sun. We came up with things like Democritus was the one that came up with the idea of atoms existing. And I think it might have been Anaxagoras that suggested the sun was at the center, and that sort of thing. But this model worked for a long time. The problem was once we realized that, like in, let's say, June or something, you might see a particular set of stars that look like a mirror image of each other. And then one year in June, that classic image is there, and there's this new star in there that looks really odd, like it's never been there before. So you keep an eye on it, and you notice over the next 2 weeks, that little extra star seems to do a little loop-de-loo like that and goes off into, a long way away from that familiar pattern of stars. That's basically some of the motion that was going on. Those particular stars were given special names. They were called planetos, which is Greek for wanderer. And we had to make explanations of that. And Aristotle, going on his infinite logic and his obvious premises like the heavens are perfect, ergo everything in the heavens are perfect, ergo the perfect shape is a sphere, ergo every shape in the universe in the heavens must be spherical or in 2 dimensions circular. So that does not seem like that good of a premise to us, but then at that time it seemed very, very obvious that had to be the case. So clearly all of the planets were in fact sort of embedded in crystalline spheres, and therefore they moved in some kind of spherical motion. But if you have something like those planetos doing a loop-de-loo, it's hard to explain that while keeping it on a sphere. Not only that, Aristotle had the other rules that the heavens are perfect, so they're immutable, which means they can't change. I think that's what immutable means, but anyways, they can't change. And that means they can't slow down, because if they slow down, that means they slow down from the perfect speed to an imperfect speed, which means the heavens are now imperfect, so that can't be right. Or they slowed down from a imperfect speed to a perfect speed, but that meant the heavens were imperfect for a bit of time, and that's not acceptable either. So that was their logic in saying that the planets, the things in the heavens, everything in the heavens could not change. It had to be If it's going to actually move, it had to move at a fixed rate. If it's going to move at that fixed rate, that movement better be a straight line or a infinite, or excuse me, a sphere, or obviously the two-dimensional representation of a sphere is a circle. So that's how we got the orbits that we did. But when we tried to fit that to nature after hundreds and hundreds of years, we would go back and look and try to predict where the planet's going to be in years in the future. And looking at like the last atlas, say, that someone made of the stars that was made maybe 20 years ago, you had 20 years of data that they didn't have. You tried to fit that and you'd fix the model to make it more accurate with the latest data. So they would adjust things like how big is the sphere, how fast is the planet going around the sphere, and so on and so forth. And they even had to ultimately move centers and stuff like that. So there was an equipoint and all sorts of weird stuff. And there was epicycles and deferents. So in order, for instance, to make up for the little loop, what they imagined was going on was there was a deferent, which is a spherical shell around the Earth. And then, like, if we're talking about, for instance, Jupiter or Mercury, excuse me, not Jupiter or Mercury, Venus or Mercury, then what we knew with those is Mercury never got very far from the sun, like on the order of 30 some degrees, and Venus never got more than like 42 degrees. So how do you explain that? Well, you explain it, or they explained it, by imagining a deferent, which is a giant sphere centered on the center of the Earth, which later became the equipoint, and the Earth moved over, blah, blah, blah. But that's the way you would do that. But that still doesn't explain the back and forth. So then you had to put an epicycle on that deferent. So an epicycle is yet another sphere, the center of which lies on the edge of the deferent. So you got a sphere on a sphere. And what was happening is when the planet came on the closer side of the epicycle, that was when it was closer to you. That explained why the planetos, got actually quite bright when it was going in what we call retrograde, the backwards motion. And then when it came around the other side, it got darker again because it's slightly further away. So they figured out a way to make sense of Mercury and Venus that way. And then they found Mars and Jupiter were doing the same thing, except, they could get any number of degrees away from the sun. So they didn't have to have their centers of their epicycles on a special line that connected the center of the Earth to the center of the sun, like Mercury and Venus did. But these things still had to make sense of the loop-de-loo that it did. So they'd put, again, another epicycle and deferent together and adjust that. That all worked, and you could consistently predict it years in advance. And that's how these people like Kepler, Galileo, Tycho Brahe, well, he had other means too, but these various people that were doing this kind of work were basically gifted enough that governments would pay them to make up astrological atlases, if you will, so that they know exactly where the planets were for the next 10, 15, 20 years. We don't have a very good feeling for why a government would do this right now, because we're not so in touch with it. But imagine, in a time when your only thing you knew was sort of when the seasons were, and then you had very specific religious holidays or holidays in general that were tied to astronomical information. For instance, even our modern day Easter, you've all noticed, hopefully everybody's noticed now, that Easter doesn't come on the same day every month. In fact, it has to always come on a Sunday. That's a key. But it also has to be after the summer solstice. It has to be after a full moon, a bunch of different things like that. I encourage you to look up how we pick our Easter every year. But in doing such a thing, the government would have to be on board and plan out all those things. Not only that, there was this pseudoscience called astrology, and they believed that like a science. Like they had astrologers that would advise them, hey, such and such is in this constellation at this time, so it's really a bad omen for you to do this, or something like that. So they had to make up all these things, all these different stories with regards to this positions of the planets at various times. So that's how they made their money. But it became really, really complicated. In fact, I think it was there's a quote where Kepler wrote to Galileo, and he basically said, if I had been there when the Lord made the universe, I would have asked him to make it a little less complicated. So actually, when it was all said and done, by the time Kepler comes along, we had something like 60 spheres inside of spheres inside of spheres, and it was a holy nightmare. So what ultimately happens is Copernicus, who I consider an entirely separate entity from the scientific revolution, there is a Copernican revolution that I see is more like us realizing that we're not the center of the universe, we're not everything. And then there's a scientific revolution where we learn about applying science and reason and experimentation and stuff like that. The reason I separate those is because actual Copernicus, when he came up with his idea to put the sun at the center and the other bodies orbiting it, it was purely because he said we had lost our way from what Aristotle taught us. So he really wasn't using what I would argue is science and the trueness of science. He's really appealing to authority. So we sort of leave that out. But either way, it was a simpler system. He had managed to put the sun at the center, and then there was a very good and understandable reason why Mercury had the shortest period, and then Venus the second shortest, and so on and so forth. All sorts of stuff fell right out of it. Uh, in the meantime, it was apparent that both the heliocentric model and the geocentric model were able to make predictions, and they were pretty good. So the problem was, which one do we choose? Well, around this time is when Kepler is a tutor, and he's like literally teaching one day in class, and he's talking to all these kids. And basically, he comes up with an idea. He's sort of a not the best of instructors. He's sort of like me in that, I get drawn off to the side for some story that may or may not be related to what we're talking about. Yeah, that's him. So I'm picturing him like explaining his theory of the universe to the 4-year-olds and 15-year-olds all at the same time. But either way, he actually had said, well, there's no way that God would make this universe with the bodies that we know of in the heavens, and those bodies are exactly the right number for us to have each of those bodies separated from one another by one of the perfect solids. He's like, that can't be a coincidence. So his model was literally celestial spheres like Aristotle would have had for each of the heavenly bodies: Mercury, Venus, the sun, Earth, Mars, all that good stuff. But what separates one sphere from the next is one of the perfect solids. So this is some sort of ancient geometry stuff, but dodecahedrons and things like that's what we're talking about. So he immediately starts working out this model, and he sends it to all his friends and people in the sciences, one of which is Tycho Brahe, which I think is pronounced Tycho Brahe. He's a Dane. He's from Denmark. It's kind of a hard name to pronounce, but this dude was like doubly royal. He was a big fat guy a big, strong, fat guy. And this is back in a time when fatness meant you were powerful because, you actually had enough food where you could eat and be fat. So, so it made you super powerful. But he had like two bloodlines of royalty, and he was really good at sweet talking people and getting them to give him money. So he managed to get his king to give him an island, and then basically allow him to collect the rents, and he could use the rents to build his scientific machinery and stuff like that. So that's what he did. He owned an island that's called, consonant, 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 vowel, consonant. It's actually not quite that bad. It's like HVEEN or something, but that was the island. And he was not necessarily a good landlord. Like, he was really mean. If it's the middle of the winter, you're 4 foot of snow, yeah, he's gonna kick you out. He don't care, right? So he's not that good of a guy. He got a moose so drunk one night that it fell down several flights of stairs and broke its neck and died, which is sad. He had a pet human, what we'd call little people nowadays, or people of height difficulties. I'm trying not to use the non-PC words, and I'm also thinking about a skit I heard this weekend about one of the non-PC words, so I'm not going to do that either. But anyways, that's what that's what we had. He also just partied all day and all night. And I don't know if you know this, but royalty, they don't really poop or pee, so he never had to do that. No, that's completely false, of course. So one day he's partying after he's now hired Kepler. He did manage to pick up Kepler, and Kepler's sort of this character that's like I consider Kepler to be sort of like modern day Mike Pence. Just, you know, how straight and conservative he is, in the true faith of God sense. Not, I'm not talking politically. I'm talking just a true good, quote unquote, person who's trying to do the best thing he possibly can based on his understanding of his religion, that sort of thing. That's sort of like Kepler. He's really brilliant and really just devoted to Christ and his sort of thing. Then there's Tycho Brahe, who's more like Russell Brand, who was married to Katy Perry, or some other modern day stoner, maybe from Pineapple Express or something like that. Try to think of the most biggest party animal you can think of. Well, that's what Tycho Brahe was. And he hires this guy, and the guy gets there, and as I told you, the royal do not poop or pee. But anyways, he is partying one day, and rather than get up and let the world know that he is a mortal man that must poop and pee like everybody else, he refused to do so, and his bladder burst, and he became septic and died of a horribly nasty death in a rather quick time period. It's a really terrible thing. Still, his lack of respect that Kepler had for him, he really respected his prowess as a scientist, and for good reason. He was really, really good. Without the aid of a telescope, he had basically just a ginormous protractor like built into the wall that he could read to really high levels of precision. He made a lot of work to make sure he could figure out times really well and stuff like that. And he really cataloged a lot of good stuff that we hadn't seen. He managed to not only catch a comet and you know, get to see it and mark it out its path and all that stuff. He was actually able to discern how far away it was, which is pretty remarkable. Because of course, depending on what you define as the heavens, they either start right outside our atmosphere or just outside of the orbit of our moon. And he was able to find that they were very much inside, the comet was very much within our solar system, and therefore in the heavens and outside of our moon's orbit. So that was kind of a big deal as well. But he needed someone that could help him with the math, because he had made up his own model, which is really a weird one. But imagine that everything but the Earth orbits the sun. Okay. So just like reality, we're going to have the sun at the center, and then we're going to have Mercury orbiting it, and then outside of that is Venus, and then outside of that we're going to skip Earth and just go right to Mars, and then Jupiter, and then Saturn. And that was sort of his model of the universe. Only the Earth was over here, and the center of that system was the center of the sun, and that would orbit around the Earth. So that was Tycho Brahe's crazy model. And he was having a hard time doing the mathematics of that, which is a little bit ironic because, as I mentioned, got ready to mention to you earlier, he actually has no nose, and it's because he lost his nose in a sword fight over who was the greater mathematician. Now he's weeping about not being so good a mathematician, so he hires Kepler to come work there. And once Tycho Brahe is out partying and has this horrible incident, he ends up dying. Kepler then fights in court to get the data, and finally is able to conduct his experiments. So, or his analysis. And what he does is he has to throw out his own model. His perfect solids model was crap. It didn't work. And like a good scientist, no matter how much work you put into it, you just throw it, right? Maybe that'll be fun for something later. We can make a physics problem out of it and make students hate you or something like that. Now, the other thing was he found that the Copernican model didn't work. Copernicus' model was good, but it required circles. Remember, he went back to Aristotle's ways because he thought we had lost our way from Aristotle. So he put circular orbits. The planets didn't speed up or slow down or any of that kind of stuff. So that one didn't work either. Brahe's model didn't work either. So finally, he had to go brute force and just figure out a way. And he found out three laws. The three laws, I'm just going to say them. You can copy them later. But the first law is the planets sweep out, or excuse me, the planets orbit the sun in elliptical orbits with the sun at one focal point. So you probably know how to make a circle with plywood and a nail and a pencil and some string. And this is sort of like that, but you need two nails. So as you put one nail in and then draw a string, tie it to the nail, tie it to the pencil or chalk or whatever, hold it tight, and that would make your circle. when you're doing an ellipse, what you want to do is put 2 nails in the plywood and then connect it with a string that's longer than the distance between the 2 nails. And then you pull it taut like this, and it traces out an ellipse. And what he said was the planets actually sweep out ellipses with the sun at one focal point, and that means the place where one of those nails were. Now, this is really ironic and crazy because he's able to figure out that this is not oval, which we don't have a good mathematical definition of necessarily. He said elliptical, and he was right on the money. It actually turns out it has to be specifically an elliptic shape. So he had worked that out and discovered that, which is pretty good. And it's even more impressive when you realize that if you put even, let's say, Pluto's orbit, which is the most eccentric, the most elliptical of the orbits of the non-planets, even, or well, not of all the non-planets, but at least of all the planets, including what used to be a planet, Pluto. So that one's one that's not very circular. And if you put that right next to a circle of about the same size, you couldn't probably, unless something really special about you, you probably could not look at that and see which one was the circle and which one was the ellipse. That's how tight what Kepler figured out was about our stars, about our orbits of our planets. Specifically, the ellipses were so closest to circles, but he was still able to figure out that they were ellipses. So that's pretty impressive when it's first in the first case. The second case was Newton or Kepler's second law, which basically says the planets sweep out equal areas in equal time. So if you imagine like tying a string to the nail that the sun's at, and you look at the planet at one place, and then you see it sweep out a pizza slice at some other place. If that sweep took 30 days, then if you find another pizza slice anywhere else in the orbit that has the same area, then that one will also take 30 days. So that's kind of a big deal. It's definitely showing that the planets are speeding up and slowing down, very different from what Copernicus had. But the planets sweeping out equal areas in equal time is Kepler's second law. And then finally, Kepler's third law is the square of the period is proportional to the cube of the semi-major axis. Again, all of this wording is in your book. I'm just sort of giving you a quick rundown of the history and the story of it. Okay. So Kepler was able to derive these laws, and they're purely epistemological. He doesn't have any idea of why these are the laws. He just knows that this does work. And he doesn't really know necessarily that it's a law. He just, knows it fits the data, right? Now, when Newton comes on the scene and discovers a formula for gravity, then he can actually take his calculus that he invented and his formula for gravity that he discovered, and can then prove all of Kepler's laws and exactly why. So he's able to explain specifically that, yeah, the orbits of things around any bodies are only closed for a 1 over r squared force, or for a F equals k times x force. Those are the only types of forces that allow closed orbits. That's a pretty big thing. Also, when something does orbit it, it's always going to form what we call a conic section. So it's going to be either a parabola, a hyperbola, an ellipse, or a circle. That's pretty much all it can do. And that's actually the equivalent, or even more specific than Kepler's first law about the planets orbiting in elliptical orbits. And then he can actually use the conservation of angular momentum to show that the to show that the area swept out in equal time is purely a result of conservation of angular momentum. So that's pretty impressive. Finally, you can use, and we can use, energy methods if we really wanted to, but he could also use mechanics, which is what Newton did, in basically just showing that the only way the orbit works is if the square of the period is proportional to the cube of the semi-major axis. And I always treated that one as a law that's really easy to understand from a conservation of energy standpoint, not so much from anything else. So anyways, that's the 3 Kepler's laws. Now, what happens after all this? Well, Kepler's right. It works really well, but again, we don't really know why. Then Newton comes on the scene, and Newton basically he writes basically that he's sitting under an apple tree when he looks up and he sees an apple and he sees the moon and says they're sort of the same. I'm wondering if that they're the same thing. Which by that what he means is it is it the exact same force that's going to take that apple, and once it gets so heavy that the stem can't hold it, it's going to break loose and fall? Is the force that pulls that apple down to the ground, is that the same as the force that causes the moon, which would otherwise just go straight, but makes it curve inwards towards the center of our Earth so that it maintains a nice nearly circular orbit around our planet? Uh, he thought maybe it is. That's probably what the origin of this force is. And he knew that on the surface of the Earth, the distance from the center of the Earth to the surface is 1 Earth radii. And at that point, the acceleration due to gravity was 9.8 meters per second every second. And then he said, well, the moon is way out there, 60 Earth radii away. And I need to figure out its acceleration. Well, we know that if you want to make something go in a circular orbit, the acceleration it needs is, anybody? It's got a little lowercase c next to it. Yes, the centripetal acceleration, which we just finished in chapter 5. So v squared over r. If you actually take v squared over r and calculate that, it turns out, I'll show you the quick calculation in a second. It turns out that you get a value of 0.0027, I think 2 is the next digit, meters per second every second. And Newton says, okay, well, if there is some kind of force that he's thinking about calling gravity, if there's such a force, I wonder how that relates to the distance away. He had been studying light, and he found out, in fact, that like if you had a candle and you figured out some way to make sense of how bright that candle is, then at a distance of 1 meter away, he had a very specific brightness for a candle. But then when he went 2 meters away, the brightness didn't decrease by a factor of 2. It actually decreased by a factor of 2 squared, which is 4. And if he went instead of 2 meters away or 1 meter away, he instead went 3 meters away, then the brightness would reduce by a factor of 9, because 3 squared is 9. So he said, I wonder if this force obeys a 1 over r squared law, just like light does. And he said, well, if that's the case, well, at 1 Earth radii, the acceleration is 9.8. At 2 Earth radii, it would be 2 squared, so 9.8 divided by 4. At 3 Earth radii, it'd be 9.8 divided by 3 squared. At 4 Earth radii, it'd be 9.8 divided by 16, so on and so forth. So what would that acceleration be at 60 Earth radii? Can anybody figure that out? You guys? So at twice away, it went 9.8 divided by 2 squared. At 3 times as far away, it went 9.8 divided by 3 squared. At 4 times away, it went 9.8 divided by 4 squared. What's it going to be at 60 times the radius away?
9.8 divided by 60 squared.
Exactly. 9.8 divided by 3,600. And if you do that, you will notice that you'll get exactly the number that I just finished telling you, which is what we got for v squared over r, namely 0.00272. So when Newton does that calculation, he realizes, hey, at this instant, I'm the only person on planet Earth that has any idea why Mercury orbits the sun. Why does Venus orbit the sun? Why does the Earth orbit the sun? Why does the moon orbit the Earth? He's the only person that knows that. It's a really monumental moment. So that's the whole spiel of the history of this. So now let's go ahead and use this and show you what the actual results were. Okay. Anybody have any questions on it before we go on? All right, I'm going to go ahead and share my screen with you real quick, and we'll be able to make some sense out of this in a second. Once you see some of the equations, you'll see it's actually pretty straightforward. Okay, so we had already talked about centripetal acceleration, and specifically what we know is A sub c is equal to v squared over r, right? So when Newton was thinking about the acceleration that the moon must have to stay in a circle, he had to work out the details of v and then v squared over r. Well, v is just the circumference of the moon's orbit, which is 2 times pi times r, divided by the period of the moon's orbit. So that seems pretty good. The big deal is, of course, that the moon's orbit is actually 60 times the Earth's radius. So I'm going to use that. So I'm going to say 2 times pi times 60 times 6.378 times 10 to the 6 meters. That's the radius of the Earth. And then that's 60 times the radius of the Earth. And then here's the weird part you might not be that familiar with. But the month that we're referring to here, or the period that we're referring to here, is I'm expecting that the moon can make a distance of 1 orbital circumference in 1 orbital period. And the orbital period for the moon is the time required for it to go in a specific direction in space from the Earth to that same direction in space, not from new moon to new moon or anything weird like that. This particular period is 27.3 days. And then, of course, 27.3 days, we can't use days for the unit. So we have to do, I'll actually put the unit on here. We'll say 27.3 days. And then we'll say 1 day is 24 hours. And then we'll say 1 hour is 3,600 seconds. Now, when we do that, we can get a speed that I think is kind of interesting to know already. So I'm going to do this as a whole separate calculation. So I'm taking 2 times 3.14159 times 60 times 6.378 times 10 to the 6th. That's 2 pi times 60 times 6.378 times 10 to the 6th. That's the numerator. I'm now going to hit divide by parentheses 27.3 times 24 times 3,600. Close parenthesis. And that gives me 1,019.4, 1019.4 meters per second. Now remember, that's I think a meter per second, something like 2 miles per hour or something like that. So that's pretty darn fast. Okay. Now that we actually are using, I should probably call this 3 sig figs. So this 9 and the 4 are not real sig figs. But now that I have that, I can now say that the centripetal acceleration should be v squared over r. So that's going to be 1019.4 meters per second squared divided by r, which again is 60 times the Earth's radius, which is 6.378 times 10 to the 6 meters, like so. So now I'm going to take this quantity, 1019 squared. I'm going to divide it by parentheses 60 times 6.378 times 10 to the 6, close parentheses. And that gives me, yep, you guessed it, 0.002715. Oh, I even remembered the tube correctly. So 271545 meters per second every second. Okay. So that's a big deal. That is the centripetal acceleration necessary for the moon. And that's just based on our understanding of centripetal acceleration, which he had worked out already. Probably had the calculus, used the calculus that he had invented himself to figure out the formula v squared over r as well. So it's pretty good. He's got now a calculation of that and found out what the magnitude of the acceleration is. And now he's going to test his 1 over r squared hypothesis, which is, of course, if the acceleration at r equals 1 Earth radius, so implies r equals 1 Earth radii. And then what you'd say is 9.80 meters per second over what when r is equal to 60 Earth radii. So that's sort of the way I'm thinking about it. Obviously, if we step twice as far away, we're going to divide that by 2 squared. 3 times would be 3 squared, so on and so forth. So lo and behold, what we get is at 60 times the radius of the Earth, we get A is equal to 9.80 meters per second every second over 3,600. And that value is 0.0027. Let's do it to make sure I get even the right number of digits. So this is 9.8 divided by 3,600. And that gives me 0.0027. And this one goes 2222 like that. So the main thing is, look, to 2 sig figs, we actually have the value that's pretty high. Or let's say it's pretty low probability of that happening by accident. So any questions on that? Now, the good news is this is part you didn't necessarily have to be able to do your calculation yourself. This is more making sense of how he came up with it, so that you can, sort of appreciate the law of gravity, which is pretty amazing that it can be stated that simple. So what he found here was that the law of gravity does obey a 1 over r squared law. 1 over r squared law. So the way you might write that is you might say the force is inversely related, and to say inversely related, we put a denominator in, and the numerator, of course, you normally just use 1, and then that allows whatever the variable in the denominator to be, that's the one you're inversely related to. So he was pretty confident that the force of gravity would be inversely related to r squared, and then he went on further and said it's a universal law of gravitation in a couple senses, one of which is that any 2 masses, if they have mass, are going to attract each other. So in that sense, it's universal no matter where you go. If you have mass, you're going to have a gravitational force. What he realized is that that force should be proportional to the product of those masses, M1 and M2. So that's ultimately how his law came about. Once you do a little bit of experimentation, as Cavendish did, you can ultimately find that the answer is, remember, if we ever have a related to or proportional to, like that little fish symbol, the way you get rid of that fish symbol is you replace it with an equals and a constant. So in this case, the constant ended up being what we use a capital G for, and then it'd be G M1 M2 over r squared, where G is a very, very small number. It's 6.67 times 10 to the negative 11th. That's newtons meters squared per kilogram squared. So this is literally a number that is like 0, the decimal point, and then 10 zeros, and then a 667. It's a really, really small, weak number. That's why gravity is really a weak thing. However, it's also a very strong thing. And again, they call it the universal law of gravitation. And the reason why, another reason why, is if you look at this formula, there's literally no r you can put in there in which the force becomes 0. So every mass in the universe is putting out a gravitational force, and that gravitational force can reach across the entire universe. So it's a kind of a really big deal, right? Now, he goes on to say, of course, if you imagine, like when you're talking about the planets, the individual diameters of the planets is so insignificant compared to the diameters or radiuses of the actual orbits. So if you think about it that way, then the planets are sort of like point particles. What he tells us is if you have basically point particles, then r is just the distance between the point at which m1's at to the point at which m2's at. That's actually the distance r. Now, in addition to that, the line of force of attraction will be parallel to that line. So if you imagine a line going from the m1 to m2, the force is either going to be from m1 towards m2 on that line or from m2 towards m1 on that line. So that was kind of a big deal too, but that gives us the ability not only calculate the magnitude, which is what this formula does, but also tells us the direction. He goes farther though, and he basically shows us that if you have, for instance, a spherically symmetric mass, then it's going to behave just like a point particle at the center of that spherically symmetric mass. So now you can just take this formula and just apply it to spheres, as long as you can assume their mass is fairly uniformly distributed throughout the sphere. So that's what Newton's law of gravity is. And like I said, once he's got this equation, he immediately tries to make sense of Kepler, and it can prove, in fact, that the orbits are elliptical. Specifically, he's able to expand it a little bit and say that all the orbits are actually conic sections. So anything orbiting anything is going to orbit in a conic section, which is a pretty big deal. He's also able to say Kepler's second law, which is the planets sweep out equal areas in equal times. That's basically related to angular momentum conservation, which we'll learn about later, but it's basically the reason why ice skaters speed up when they bring their arms closer to the center of their body, and then they slow down when they bring their arms out where their hands are sticking farthest away from their body. That's basically what he was able to show it was equivalent to. And then ultimately, the third law is the square of the periods is proportional to the cube of the semi-major axis. That one, t squared, is proportional to the semi-major axis cubed. That's Kepler's third law. That's one that's obviously in an equation form. The good thing is, if you happen to use t in the units of years, and you use a in units of astronomical units, which is what the Earth is defined as, one astronomical unit is our radius of our orbit. So if you do that, then by that point alone, remember how I just finished telling you how you can replace a proportional symbol with an equals just by adding a constant. That's what we can do here. But check this out. We know one data point. Can anybody tell me what the period of the Earth's orbit is in years? Your speaker's not on, Jennifer. You look like your mouth moves, maybe. It doesn't say you mute.
365.
Yep, it's 365 days, which is 1 year. So yeah, in this case, you would replace t with 1 for the Earth. How about astronomical units? Do you know, does anybody know what our orbital radius is in astronomical units? It's actually the definition of it is our orbit. So it's literally 1 again. So if you put 1 and 1 in there, then clearly we now know that the constant is 1. So we don't have to put any other number in there. We just have to put it equals. Now, what's going on is there is a number there. That number is 1 astronomical unit cubed over 1 year squared. But that's basically it. So anyways, that's a version of Kepler's third law. You can actually do it as well by setting Newton's law of gravity, G, mass of the planet, mass of the star, mass of the planet, over r squared is equal to m v squared over r squared. If you actually work this out that way, and you replace v with 2 pi r over t, you'll actually get Kepler's third law with the constants in it. You'll see it in your book. There's also a chance for you to do that for extra credit, so I'll leave that to you. I also wanted to show you what an elliptical orbit looked like, just so we could understand sweeping out equal areas and equal times. So again, we'd imagine putting a nail in a piece of plywood and another nail in a piece of plywood, and then we attach a string to the two nails, and the string's got to be longer than you. Hey, sorry about that. Had a dog attack another dog. I'm sure there was some food involved. Anyways, sorry about that. So if you pull that string tight now, and as long as its length is longer than the distance between the nails, then you can actually pull it tight and hold your pencil right in there. And in principle, it's supposed to work out a shape like this. Now, doing it is a lot easier. Oddly enough, it's actually a lot easier doing that with an actual nail than it is with doing it with just a pen and paper. But that's supposed to be what the ellipse looks like. That would mean that the sun would be, say, here, and there would be nothing at the other one. And if you're at this point, if your ellipse is this dramatically different from one side to the other, then a 30-day orbit might last, let's say, like this. So this would be day 0 and day 30. And what Kepler said was the planets sweep out equal areas and equal times. So if you imagine a really long slice of pizza, then it can't be very wide because it's so long. And what you see is this might be day 0 and this is day 30. So this is telling us specifically that the planets actually go quite a bit faster when they're closest to the sun than they do when they're farthest from the sun. So that's a, interesting thing all beside itself, but it's also, way beyond what Copernicus was saying or willing to say, because Aristotle still thought they had to go a constant speed. So that's a pretty big deal. But like I said, that is Kepler's second law, and of course that includes his first law, because his first law is that they sweep out or that they orbit in elliptical orbits with the sun at one focal point. By the way, this distance along here, that is called the major axis. And it's both the name of the thing, but it's also the name of the variable for how long it is. And this right here, dead center, this thing is called the minor axis. Okay. And when we're talking about, for instance, the square of the period is proportional to the cube of the semi-major axis, what we mean by semi-major is half of the major axis. So basically what we're supposed to be imagining is this is A, the semi-major axis, and this is also A, like that. So just so you understand what that's about. Now, all we have to do is work some problems with this Newton's law of gravity. And as I said, Newton's law of gravity is just F is equal to G M1 M2 over R squared. So the first thing you might think to yourself is, well, how big is that force? Does Mr. Younger, he's kind of the biggest person I've ever seen in my life. So would he be like gravitationally big enough to pull on me? Well, let's check that out. So let's say the force between a student and someone the same size as Mr. Younger. So that's going to be 6.67 times 10 to the negative 11th. Whoa, almost put negative 70. Negative 11th. That's Newton meter squared per kilogram squared. That's the G, in other words. Now, I'm going to tell you that I'm probably a good 110 kilograms. So that's going to be 110 kilograms. Now, a normal person that didn't, eat a couple small children or something, maybe they only weigh 60 pounds or 60 kilograms. So we'll put that in there too. And then let's say we're going to be about 30 centimeters apart. Now, let's make it 50 centimeters apart. Okay. So we're going to put them about 50 centimeters apart and see exactly how large of a force that would be. So 50 centimeters is the same thing as 0.50 meters, and then we got to square that. So now I can put all these numbers in and pretend like my fingers aren't so fat that they're going to miss every key, but 6.67 times 10 to the negative 11 times 110 times 60, and then divided by 0.5 squared. And that gives me a really itty bitty 1.76 times 10 to the negative 1, 2, 3, 4, 5, 6. 10 to the negative 6 newtons. Now remember, in Newton is already a quarter of a pound, so it's really small anyway. So we're talking 1/1,000,000th of a quarter of a pound. So yeah, the force of gravity is not that impressive in terms of strength. You have to get really huge masses and ideally have them fairly close together. So what's a good example? Well, let's try another one. So this was an example of two people. Now let's try another example where we're going to do the sun and the moon, the sun and the earth. So sun and earth. Let's see what kind of force that is. Now, is that going to be a big deal? Okay, well, we'll have to calculate it. What we have is 6.67 times 10 to the negative 11th newtons meter squared per kilogram squared. Now what we need is the mass of the earth, which actually I had written it down, but now I can't remember where it is. So that's not working out great for me. Wait a second. I found an example right here. I was going to Google it otherwise. Ooh, that's not it. I want to say it's 5.24 times 10 to the 24th or something, but that might not be it. Okay, I'm going to Google it. So clearing this mass of the earth. The mass of the earth is 5.97 times 10 to the 24th. So 5.97 times 10 to the 24th, and that is kilograms. And now we'll do the mass of the sun. I'm pretty sure that's 1.99 times 10 to the 31st kilograms. Let me double check it just before I commit. Mass of sun. And it's 1.9 times, times 10 to the 30. Glad I checked myself. So it's 10 to the 30, not 10 to the 31. Sorry about that. And everything else looks pretty good on there. Now what we need is the distance of one astronomical unit, which I think I know, but I don't think I want to risk it. So I'm going to take now I'm doing the search for the astronomical unit. There it is, 1.496. 1.496 times 10 to the In this case, it's million kilometers. So that'd be 6, that's 10 to the 9th, 10th, 11th. That's right. So times 10 to the 11th meters. And now we're going to square that. So I just, in real time, obviously y'all saw y'all saw it with all the excitement there was in that. I just Googled each one of those things just to find them out. They are in the front cover of your book, but I didn't have a textbook with me. So 6.67 times 10 to the negative 11 times 5.97 times 10 to the 24th times 1.99 times 10 to the 30th. And all that's going to be divided by 1.496 times 10 to the 11th. And we'll call that squared. Plus we're supposed to. And I get, in this case, a pretty significant force, 3.54 times 10 to the 22 newtons. So, yeah, that's a big force. Of course, it's a long way away, which is really impressive because if it's closer, it'd be even bigger. But imagine that 3.54 times 10 to the 22nd is the order of magnitude of the force between the Earth and the Sun. That's the force that's required to make it maintain a nearly circular orbit. You're actually not too terribly far off by treating the Earth's orbit as if it were a circle. The big thing to remember is gravity, like any other force, they just add up. So if you had, an assortment of masses in various points in space, and you wanted to find the force on one due to the others, you just calculate the force on one magnitude-wise using the formula, figure out some way to represent the direction of that force, then do it for the next, and then just add them all up. So we actually can easily just add one gravitational force to another gravitational force, and the only rule is that we add them like vectors. Anybody have any questions on that? All right, your book does take the time to do this. I have wanted to do this a lot, but basically you can take Newton's law of gravity and put it in a vector form. And this 5th edition, they went ahead and did it. I don't think that, I'm pretty confident they didn't have that in the 4th edition. But anyways, they did do it this 5th edition. And I don't know, I have never found it that useful in this semester. But if it helps you, then by all means use it. Or if you see a problem in there that you find interesting, but you just don't understand or something, let me know. I'll choose to work it, but I'm basically going to avoid that section for right now. When I get to the 242 class, you'll see that we do this with a lot of things. We take a lot of forces and turn them into vectors. Well, I shouldn't say twice I have to do it for 2 different laws, Coulomb's law and the law of Biot-Savart. So you'll get plenty of that later, but this is also something to come back and look at once you've done that. It might actually help you then. But normally it just requires you to come up with a vector that connects the 2 particles together. And if they're not particles, then you have to start dealing with either adding up all the individual ones or just treating them as if they're point particles at the center of mass. So that's what this is saying right here, is just you add up all the forces. So sorry, I was just looking at the screen for a second, explain it to you, and completely didn't even share the screen. So that didn't help you at all. Anyways, I was thinking about how much time I had left. I don't have I got another 20 minutes, but at the same time, let's see. Oh, okay. Here's something else that I wanted to cover for you, and I think this will work pretty nicely. So in addition to these types of examples, we've just found out, for instance, how to calculate the magnitude of the forces. But what you might also want to figure out is why exactly is our weight that we experience, why is that given by the formula it is? Or more specifically, what does that G equal 9.8? What does that have to do with Newton's law of gravity? Well, if we look at it from a Newton's second law of motion standpoint, you could say the summation of all the forces on an object is equal to the mass of the object times the acceleration of the object. Now, if you actually wanted to treat the force causing the actual acceleration as a gravitational force, then you say, okay, well, the force is going to be equal to G times the mass of the Earth. Remember, this is the symbol for the Earth, times the mass of the, let's say, planet or whatever you're wanting to work on, divided by the square of the distance between them. That is Newton's second law, or excuse me, Newton's law of gravity, but we can now put that in, for instance, for the equation of weight equals mg, right? If we assume, for instance, that our weight is due to gravity, then it makes sense that our force of gravity should be equal to mg as well. So now I can take this same W instead of equal to mg. We'll skip the summation of the forces, Newton's second law. I was going to work it another way. I changed my mind at last minute. But this way, we're going to put the mg here, and what you see happens is that the lowercase m, which would represent like the planet or me or whatever, that would basically cancel out. So evidently, based on this, gravitational acceleration should be equal to the gravitational constant, g, times the mass of the planet that you're actually on, divided by the distance you are away from the center of the Earth, which is generally the radius of the planet. So I'll say R plus like this squared. So that should, in principle, be equal to G. So let's check that just as a calculation. We're going to say G equals, with a question mark over it, 6.67 times 10 to the negative 11. I don't know why I keep wanting to write a 7 there, but times 10 to the negative 11 Newton meter squared per kilogram squared. Got a person came in. Okay. Times the mass of the Earth, which I think we just found out was 5.97 times 10 to the 24th kilograms. And then we're going to divide that by the square of the Earth's radius, which is 6.378 times 10 to the 6 meters. Of course, we're going to square that. And what do we get? And of course, hopefully you guys are trying this as well. Ten to the 6, I squared that, and lo and behold, I get 9.788 888 even. Ooh, 3 8s, and then a 3, and then a 7. So anyways, that is what gravitational acceleration is due to. So obviously, if you know the gravitational acceleration of another planet, you could use that to discern the radius of the planet, or you could use it to discern the actual mass of the planet. Or if you had the mass and the radius, you could figure out what the gravitational acceleration on the planet is. I'll tell you a neat one is gravity on Jupiter. If I remember correctly, that's like 27.9, 27.8 meters per second every second. That's, basically 3 times our gravitational acceleration. So give that a try. See if you can come up with that calculation. Anybody have any questions on that? All right. I think I've already done the other part. Okay. Here's a neat thing. I actually offered this as an extra credit, so you should see it in your modules. But one of the extra credits is kind of neat. If you took and determined the acceleration of gravity, notice we found G is equal to G, the big G, times the mass of the Earth divided by the distance from the center of the Earth to the surface of the Earth. That's what that radius is, right? Well, I think you can realize from that, if we're at the top of Mount Everest, the R is bigger than when we're at sea level. And in fact, the R is even smaller than that, or even at what we had at sea level, if we go down to the bottom of the Marianas Trench, for instance. So what I usually get my students to do as an extra credit, if you want, is you can go ahead and calculate what is the difference between the gravitational acceleration at the peak of Mount Everest, the highest point on Earth, and at the other point would be at the lowest point on Earth. And then you do like a percent difference calculation just to see how far off you are by using 9.8 everywhere on the surface of the Earth. So if you'd like to try that, I'll make sure it's written up and I'll adjust the due date. But it'll be in your module for like week 7, whatever week this is. So anybody have any questions? All right. Well, I think that's pretty good for right now. I will probably work some more problems with you next time from this chapter, and then we'll just move on to the next chapter. But I'm going to go ahead and let you guys go now. So if anybody has any questions, just stick around and I'll wait for the last person to leave. Other than that, you guys are free to go. Don't make sure you did chat me your first and last name too. I think everybody already did, but I just want to make sure. Thanks for coming, everyone. See you, Jennifer. Hey, Tracy, did you have a question for me? I did see your I think you sent me an email this morning, or maybe it was late last night, but anyways. Might not be here, so I'm gonna stop my share and then stop my show. Good night, everyone. Bye-bye.